All right, welcome to a new day, a new lecture. Today we're going to talk about architecture, so a little more hardware, a little less assembly. So here are the topics for today, and there is a corresponding chapter of your Dive into Systems book about this. So please, I'm front-loading this reading for you so that you don't have to do too much later on in the semester, but you don't have to do it too quickly, but this is going to be Chapter 5, all right? So please start reading Chapter 5, and some of the things that I talk about today will make a little bit more sense. You can take a couple weeks to do it, don't worry. You got plenty more reading going on in the background, right? Hopefully you finished a lot of it last week, but yeah, it'll take us a few lectures to get through everything, but it's a great thing to have read first so that you're not lost when I explain it in depth later. So yeah, this is another important chapter to read and not skim. I think I switched things up again. This is another, it's like the second chapter. All right, this is a chapter to read and not skim. Let's say it like that. And I've left these links here again. I've copied and pasted them. So please click these if you have any questions about some of those assembly instructions that we talk about. So like, what in the world does add do, for example? There's a bunch of different ways to do an add instruction, and I highly encourage you to click on some of them and be like, all right, let's learn how this documentation explains things, so that when you get to fancier instructions, when I start teaching those, you'll understand all the syntax in the documentation and can understand everything better. So yeah, let's get right on into the real lecture now. So let's learn about the different kinds of computer architectures. And I have a question for you. All right, so here's two questions. I'll give you them in lightning, and like a lightning round where you can do both at the same time. But please, I highly encourage you to pause this video and go look up what kind of CPU architecture is in the computer you're using right now. What does it have? So is it 64-bit x86? Sometimes that's called x64, x86 underscore 64, AMD 64. The Wikipedia page kind of explains why. There's 32-bit x86, which can be called these other things. There's 64-bit ARM, which is what we're using in this class. There's 32-bit ARM, and there's even other things. So see if you can figure that out for your current computer that you're using day to day. And then also, if you have a phone, smartphone, tablet, graphing calculator, or even just like your favorite game console of all time, go like pick one of those and also go look up the CPU there. What kind of architecture does it have? And choose one. All right, could be something else. So yeah, if you're on Windows at least, here's how you look that up. I assume that you've searched for how to, but if you just like right click on your computer and you click properties, it should take you to information about your processor. So here's mine, and it is a 64-bit operating system, x64. So it's mine, for example, is going to be 64-bit x86, but who knows what yours is? Okay, so hopefully it was fun to figure out which one. And yeah, most computers that run Windows are x86 64-bit these days, and Macs have slowly started going into the realm of ARM. So 64-bit ARM if you're on one of those new M1, M2, etc. processor Macs. But yeah, these are starting to pick up speed, ARM. That's what we care about in this class. That's like the underdog right now compared to x86. And then there's also somebody new on the horizon. There's an architecture called RISC-V that we may end up using one day in our CSCI 45 class. It's meant to be open source. You don't have to pay money to anybody to make a CPU using the RISC-V architecture, so that could become very important in especially the like low-end electronics market one day. So okay, so there's that one. And then what about your phone, your tablet, your graphing calculator? This honestly could be something else. So if you look up maybe your graphing calculator or an older game console, it very likely could be something other than these. But an iPhone, for example, if we click iPhone and we search for that on at least Wikipedia, I would like to see if it tells you easily what kind of processor there is in here. So let's go to like the current one, 15 Pro. If you zoom in, I guess, probably on this right bar, it tells you about the processor. Let's search for it. Dun dun dun. A17 Pro, system on a chip, it is a 64-bit ARM-based processor. So most phones these days, including Android, are going to use a 64-bit ARM processor. And so that's a very likely one that you'll see. But yeah, hopefully that this discovery was interesting to you. If you look up like a fun game console, like the Nintendo 64, for example. Nintendo 64, my favorite game console from my childhood. I think it had, was it an IBM processor? I can't remember. Dun, 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 CPU, this guy. That was a MIPS processor. Ooh, that's fun. So that's another architecture that maybe you might learn about at a four-year college. So fun stuff. Hopefully that was fun for you too. But yeah, all these architectures, they're different, but at the same time they're the same. So let's talk about how they all like link together. Let's talk about this topic called the von Neumann architecture. So it's named after a dude. His last name was von Neumann. He was American though. It's just his last name, John von Neumann. He's insane. This dude did so many cool things. Like he had the life we all wish to have. He was a mathematician, very renowned, physicist, very renowned, computer scientist. In every field that he was in, engineering as well. Like he did amazing things. Sadly, his life was cut short because he died from cancer, likely due to the radiation exposure that he got from working on the Manhattan Project, which was an insane thing to take on. And he was up high while he was working on that. He was a big, like one of the bosses, for example. He's like, everybody loved him, and he contributed a lot. So, yeah, in addition to that, he created a model for computer architecture to try and like understand what could a computer do. And that model is still the main one that we use today as we're building new architectures like x86 and ARM. They all have the von Neumann architecture deep down inside of them. So we should learn about that. Yeah. So yeah, there's 5 different things. This is a very generic idea, and that's why it's like stood the test of time. But it was a good way to think about how to build a computer. So here are the 5 different components of a computer that's built using the von Neumann architecture. Okay, you got 5 things. You've got the processing unit. All right, and here's a diagram down here if you want to look. The processing unit is going down and it's executing all the instructions of your program as they come, like do an add instruction, do a move instruction, etc. Do a syscall instruction. So the processing unit is worrying about processing things. It's working on instructions. And then you have the control unit. The control unit is it goes hand in hand with the processing unit. It's driving the instruction and execution. All right. So it's telling the processing unit what to do. It's controlling the processing unit essentially. And so together, those two make up the CPU. And so in the diagram, you see that these two guys together make up the CPU. And so the processing unit is where the instruction processing takes place. And so you've got the registers where all those things are getting saved. You have this thing called the ALU that we'll talk about later. That's doing arithmetic operations, for example, in an add instruction. So important things happen there. And then the control unit is saying which instruction, like it's sending instructions over to the processing unit to work on. Like the PC, of course, is pointing into the memory, telling you which instruction you need to go and execute right now. And that like we're going and talking to memory, and the memory is giving you that instruction back. It's being placed in this thing called the instruction register, which we'll talk about more. And then that instruction is getting decoded and like executed in the processing unit. So that's the high level idea. We'll talk about that in depth later, I promise. But yeah, these first 2 pieces together make up the central processing unit. All right. Next, in a separate place, is the memory unit that's storing program data and instructions. So anything like your program as it's currently running, it's getting loaded into memory, both the instructions, adds, moves, syscalls, and data, all the stuff you're working on. So that all goes in the memory unit. So you have your big long table, addresses and values, that's sitting there, okay? So that's the idea. So like PC is pointing to some address, and you're going and you're finding it, and you're looking it up, and you're getting it back. You're getting back the instructions so you can execute it, okay? So there's that. And then we've got the input and output units, and these are very generic ideas. So like the input unit, the idea of it is like it could be your keyboard, it could be your hard drive, could be spinning tape back in the 60s, for example. And it's just some way to give data and instructions to the computer, okay? It's a way to talk to it, give input, and then output units are the same. So like you could also have an input-output unit, and this kind of gets blurred, this idea. So that's a thing. So yeah, output units, they store or receive program results. So like a printer is an output unit. It's exactly what we were talking about on like the first day. So those guys are a little more vague because they could be a lot of different things, but these first three, oh gosh, what have I just done? These first three are very important, okay? And all these guys are talking to each other on things called buses. So you got little wires running across, and you can ask for information, and they're all sending them back and forth. These are just wires, essentially, where you can send information from like the memory back to the CPU, stuff like that. So let's zoom in on those. So what's going on there? A system bus. All right, so it's a fun little name because it's like you're sending a bunch of data at once. You might as well use public transportation. So here's like a big bus. Whee! This is my best drawing of a bus. And I don't know, it's got a bunch of windows. And inside of the bus, you're putting a bunch of data. Right? You're putting ones and zeros, and you're sending it along in some direction. Maybe you're sending information from the CPU to the memory unit, or maybe the memory unit is talking back and it's sending information back to the CPU. So you have like there's a two-way street, right? You got some buses going on, and that's the metaphor. Hopefully that makes sense. All right, so it's just a communication channel. It's sending electrical impulses that are interpreted as binary values, okay, between these endpoints of communication. So like CPU's talking to memory, for example. And each of these lines, these wires, they're all hooked up to each other, but they do different things. All right, so let's try and talk about each of them. The control bus, for example, is for sending control signals, which I don't know if that's kind of self-explanatory. Maybe that's not good enough. And those control signals, what they do is they're either telling somebody to do something, they're requesting some information, or they're notifying other units of what's going on. All right, so again, I think that's very vague. So let's talk about like what's going on there. So the control unit is sending out stuff on the control bus most often. So it's this wire. This is the control bus, and it's connected to everybody. Everybody is hooking into the control bus, and one good example of using the control bus is when you want to execute an instruction. So your program counter has the address of the next place of the instruction in memory somewhere. So we have to go and talk to memory right now. They're separate places. We have to use the bus. So the control unit needs to know, like, what is the instruction? Give me the bytes of that instruction, please. And so along the control bus, it's saying, all right, I have this, I would like memory unit, get ready. I'm about to ask you for an address that I'd like you to read, because you could also write to memory, right? So the control bus, you're sending along that from the control unit to the memory unit. It's sending data that encodes the idea of, you better get ready to read, please. I'm going to ask you for an address right now. And then the address is sent along the address bus. That's where you send the address you want to read or write to. And so the control unit, again, is like along the address bus this time. It's this one. It's saying, all right, read, and here's the address. Like address, I don't know, 0xFF or something. Who knows? It's some address that you want to read to from. And then finally, the memory unit's like, all right, you have an address. You want to read from it. I understand what you want. I'm going to send information back to you. And so the data bus is the third place for transferring data. All right, so like both of these are going in this direction, and then the memory unit is sending something back in the opposite direction. So it's like, all right, I've got the memory you want. Here it is, and it's placing that the bytes of the instruction, for example, in this place. It's a special register called the instruction register. You could also load into other registers, like, all right, the data along the data bus is going to be placed into maybe, I don't know, X0, something like that. All right, so that's a better example, I think. But yeah, these are two-way streets. You can't use them both at once, though. They're like it's a one-way street if you're talking in this direction, and like the memory unit can't be talking back along the address bus, for example, when the control unit's trying to talk to it. So it's one direction, and then it eventually switches later. I promise that we'll talk more about that. But yeah, that's buses in a nutshell. And yeah, let's talk about architectures at a higher level now. All right, so I don't know if I think I told you that the word ARM, right? The acronym for ARM was, what was it? Advanced Risk Machines. That's what it is now. It used to be Acorn Risk Machines. So RISC, what's that word really mean? It stands for, that's an acronym. It stands for Reduced Instruction Set Computer. All right, and so in architecture, an instruction set architecture, like ARM, ARM is a RISC architecture. Any RISC architecture is all about reducing the number of instructions. It's trying to be simple. All right, it's supposed to have a small set of basic things, small set of basic instructions, and those basic instructions better be able to be executed pretty quickly. That's the whole idea. If they're so simple, you should be able to do them faster, so you can make the processor faster. All right, so that's the idea there. And then in a RISC machine, for ease of execution, every instruction has the same size. So in our ARM processor, for example, or 64-bit ARM architecture, every instruction is 32 bits long. Okay, so that's interesting. And yeah, every instruction executes in about a processor clock cycle. I know I've said those words and I still haven't really told you what they mean, but I promise we'll get there. And so like if you have a 3 gigahertz processor, that means you can execute about 3 billion instructions per second, 3 billion add instructions, something like that. And yeah, the whole job of a compiler, right, is to make assembly and then assemble it. So a compiler's job is to take your C++ code and then do whatever you wanted it to do, like some very long, complicated C++ code gets translated into a bunch of these basic instructions. That's the idea. A bunch of these basic instructions are sequenced, and those give you the higher level stuff that you really wanted to do, like somehow it ends up printing some fancy thing to your output screen or saving an image file, stuff like that. So slowly but surely, you can build up these basic instructions to do whatever computation you want done. So that's RISC, and ARM is a RISC instruction set architecture. The flip side of that is called CISC. C stands for complex this time. All right, so a complex instruction set computer uses that's what it means when you have the CISC architecture, ISA. So a CISC instruction set architecture, the instructions in one of those give you like a lot more. It's not basic anymore. It's higher level, all right, than RISC instructions. And so you have a bunch more things that you could do. Larger set of instructions than RISC, which means that in a single instruction, you could do something more complicated, which there's a trade-off between complexity and speed, and CISC is another area in that space. And because of this, you might have a bunch of different kinds of instructions that don't need to pass along a lot of information. We're going to encode it in a different weird way. So instead of having 32 bits for every instruction, they support variable length instructions. Like maybe one instruction is just a byte. Maybe another instruction, slightly more complicated, takes up 2 bytes, and you have to read from memory there and try to understand what's going on. Okay, so unfortunately, the Intel architecture, for example, x86, is a CISC architecture. It's very complicated, and so aren't you happy that we're using ARM instead this semester? And a good example of that is like a single CISC instruction. What it does is essentially it performs a sequence of low-level things, more than one basic instruction, kind of, and it may take a bunch of processor clock cycles to execute. So instead of doing one thing and doing it fast, we're doing a bunch of things, and we're trying to do it fast as well, but it may take some time because it's more complicated. And a funny idea is secretly inside of every CISC processor, like your Intel architecture, this is a very high-level idea. It's semi-accurate. Every CISC processor really, and every CISC instruction is broken down as the CISC processor is executing. It's honestly being broken down inside of the processor into a bunch of tiny RISC instructions. And the processor is doing these in a sequence. So secretly, that's kind of what's going on inside of a CISC machine. I think that's still a little bit vague, and so let's get to actual ideas here. So x86, Intel architectures. My computer right now is running 64-bit Intel x86 CISC architecture, and that means that it has variable length instructions. It is got some weird instructions that do a lot of stuff at once. And so here's an example of a CISC, of one assembly instruction in Intel land. There is one called SHA-1 RNDS4. And what that does is it performs 4 rounds of a cryptographic hash function called SHA-1, and it's very complicated, all right? And that's like used in Bitcoin, for example. But yeah, that's insane, okay? That's insane. So yeah, like I was saying here, every CISC instruction, it's essentially the equivalent of a bunch of RISC instructions in order, and honestly that's what the CPU is doing in most CISC architectures. So like in this, it's getting broken down into just a bunch of like secret RISC instructions, and there's a secret RISC processor inside of the CISC processor. So like here's your CISC architecture, and you have a single instruction like this crazy thing, and it's really getting broken down into a bunch of bite-sized pieces, but you don't get to see those bite-sized pieces. And so it's secretly RISC under the hood. So RISC wins, honestly. RISC won out, but it depends on your perspective. All right, so it's like a processor inside the processor. And so yeah, that's Intel x86 in a nutshell. That's what most Windows machines are running. And then you have ARM on the flip side of that. ARM is meant to be the dual of x86. It's the complete opposite. So it's a RISC architecture. It has different trade-offs, and it has been, over the years though, it has been extended to do complex things. Like it does have its equivalent of like video processing things, cryptographic instructions, but it still tries to keep it simple as much as it can. All right, back in the old days, it used to take RISC a bit more seriously. So, for example, there used to be no division instruction on ARM. You had to do integer division in some other way, which is crazy to think about. That's like, shouldn't that be something simple enough that any architecture could do? No, ARM said no, because division is honestly kind of complicated inside of a CPU. There is still, right? There's still no modulus instruction, which is crazy to think about. x86, of course, has a modulus instruction, so that's one thing that it wins on. But ARM is probably a better architecture to learn on, and so that's why we're learning it. And yeah, both kinds of architectures, like you have a RISC architecture that's 64-bit, that's 32-bit. You could have a CISC architecture that's 64-bit, 32-bit, 16-bit even. What does that mean? What does n-bit mean? So we've said this. I've kind of told you it has to do with registers, right? But honestly, it has to do with addresses. All right. So a 32-bit processor. The reason it's called a 32-bit processor means that it's storing or working with addresses that are 32-bit numbers. Okay. So on a 32-bit machine, the smallest address in hexadecimal is 4 bytes, 32 bits, all zeros, all the way up to the largest address is 8 Fs. All right. I feel like that should be more spaced out, like I was doing the one above. There. Like that's the smallest address, that's the largest address, that's all you could talk about. And if you have 1 byte per address, right, that tells you kind of how much memory you could possibly have. So address width and register width go hand in hand, because inside of registers, you want to use those to load from memory, and you need to have an exact address in a register, and so every register in a 32-bit processor better hold at least 32 bits. So that's why they go hand in hand. All right, that's why we, in our 64-bit ARM architecture, all of our registers hold 64 bits, because they need to be capable of holding a 64-bit address. That's what's going on there. All right, and so yeah, usually, most often, pretty much always, it's a byte address that each address represents. It's talking about a single byte in memory. And so, for example, if you were working on a 32-bit architecture, that means you have exactly about 4 billion-ish addresses, which means you have about maximum 4 billion-ish bytes that you could represent or talk about and ask for, read from and write to. So that means you could have a maximum of 4 gigs of memory on your 32-bit machine. And because this is not enough anymore these days for our memory-hungry processors, for our memory-hungry programs that we like to run, that means we needed to go to a 64-bit architecture. All right, so yeah. Moral of the story, address width and register width go hand in hand on our 64-bit architecture. That we're able to talk about 64-bit addresses, and therefore we need 64-bit registers. Okay, and so yeah, we went from 32 bits to 64 bits because we needed more memory. So 4 gigabytes is 2 to the 32. All right, 2 to the 32 bytes. That's the idea. All right, so yeah, memory got dense and cheap, and our programs were programmed very badly, and so they used too much memory, and so we switched to 64-bit. Okay, and we have some time to stay on 64-bit. All right, it's pretty much impossible to make inside of a computer and have it hold 2 to the 64 bytes of memory. That's 16 exabytes. That's way too many that any normal person could afford right now. Okay, so that's good. We have some time, and we'll stay on 64 bits for quite a while, I think. All right, and yeah, so that's that. N-bit. You know what 32-bit means. You know what 64-bit means. It has to do with the addresses that you could represent, and also the registers. All right. So yeah, let's next talk about the hierarchy of memory, because there's more to it than just registers and RAM, right? There's plenty more going on there. So here's a question for you to try. All right, go pause the video, see if you can get some numbers and understand the reasoning behind this separation. So like go to Amazon, go to Newegg, whatever the website is that people like to go to buy hardware these days, and just go like search for, put in your pretend cart, try to buy the same amount of spinning hard drive storage, try to buy the same amount of RAM, and try to buy the same amount of SSD storage. So SSDs are alternatives to spinning hard disks these days. So pretend like you want to buy about 1 terabyte of each, okay? And figure out the prices, all right? Order them from cheapest to most expensive, all right? Which one is the right answer here? Because there is only one right answer. So let's go and look for 1 terabyte of each of these, all right? I highly encourage you to try it yourself. Let's do it in a private browser because I have no clue what's in my Amazon cart right now. So let's go to Amazon and let's search for, I don't know, let's search for 1 terabyte hard drive, 1 terabyte HDD. HDD, RAM. You'll have to buy a bunch of sticks of RAM. You can't just buy 1 terabyte immediately. So, all right, hard drive, terabyte, $32. 32. That's a bad-looking dollar sign. 32. All right, let's do. You cannot buy 1 terabyte of memory, 1 terabyte of RAM. So let's do like 64 gigabytes RAM. Let's say, I don't know, DDR4, that's fine. So 64 gigabytes, I need to do math now. Python, so 64 gig, there's 1,024 gigabytes in 1 terabyte. And so if I want 64, if I get 64 at a time, I need to buy 16 of these sticks of RAM, and there's 2 of them each, and so it's $104.99, and I need to buy 16 of them. So that's about $1,700 for 1 terabyte of RAM, and then for an SSD, 1 terabyte SSD, that's about 100. Okay. Do you see why we have a separation here? All right, and I'm sure you could find it for cheaper at different places, but the order is, without a doubt, cheapest to most expensive is this one. It's D. D is the only answer here. All right, so now you know why we have these options, right? You don't just have RAM. You just don't just buy 1 terabyte of RAM and use that instead of a hard drive. There's other reasons too. But that's, yeah, we kind of just answered the question, like, why don't we just put everything in RAM? Because, like, the common consumer could never afford that. Okay, so yeah. Also, we have the concept of persistence. RAM only works when the computer has power flowing to it. So, like, when the power goes out or when you want to turn something off, you'll have a problem if you don't have persistent file storage. And that's your hard drive, that's your SSD. So persistent files you want to stick around, are stored on secondary storage, like your hard drive, your SSD. They stay there when the power goes off, all right? And yeah, RAM just gets wiped out. The power needs to be on for RAM to hold its memory, okay? But yeah, that's the idea there. And then also, like, these things, the SSDs and the HDDs, all those guys, they're connected but they're far away from the processor. I don't think I have a good example of that for you, but like they're way over here, far away from the processor. It takes a long time to talk to them, and we'll talk numbers soon. But yeah, a general rule is the farther the storage is from the CPU, the cheaper it is. So registers, for example, the kind of memory that registers inside of the CPU use are ridiculously expensive, more expensive than RAM. All right, and then RAM's a little bit closer; it's faster to talk to. Oops. And then, yeah, the downside though, there's a give and take there. The downside of buying a spinning hard drive for $32 is it's slower to get that memory, that data into main memory into a register, because you have to like have that hard drive spin and send things slowly across wires. All right. So yeah, if only we could just have a few billion registers, then we wouldn't even need RAM. Everything's close and quick. So crazy. All right. So we'll talk about the hierarchy more. We're just building up to it. Okay. And RAM is your main memory. That's your random access memory. That is your primary storage. It's the end of your primary storage. All right. Because we talked about secondary storage. What's the difference? So RAM is your primary storage. It's the end of it. Registers are also primary storage. It's the farthest primary storage away from the CPU. All right, everything after memory, and I'll give you a diagram in just a second, is called secondary storage. All right, and so the setup when you want to actually run a program is this. It's like you have your spinning hard drive, you turn on your computer, you double-click a program, you have to read the bytes of that program off of the spinning hard drive, which is pretty slow, relatively slow, and you have to copy it into RAM, because RAM is closer to the CPU. It's primary storage, it's closer to the CPU, it's faster to read from. So you copy that program somewhere into RAM, some addresses, and then every time you want to like run the program, you have to read the instructions of that program wherever they are. And so you have to read them out of memory one by one into the CPU. CPU registers. This is kind of the process when you ever want to work on data. You have to get it off of your secondary storage into main memory, and then, all right, like there's a number somewhere in memory that you want to add to and do some math on and write back. Any math has to happen on the CPU. That's where it does things, and the math needs to happen on registers. So you have to get it into a register and then write it back. That's kind of the setup. Okay, so this is much faster than this because it's closer. Okay. So yeah, every program, the moral of the story, everything is loaded from disk into RAM and then back and forth between the CPU from there. Okay. There is somewhere in between. So you can zoom in also. I don't know. What's my drawing of my best drawing of a magnifying glass? Let's zoom in on this arrow because there's something in between. Okay. It's called the cache. And the process of using a cache we call caching. All right. So a cache is all about saving stuff closer to the CPU than even the memory, because it's still a little far away. It still takes a while to access. Saving stuff even closer to the CPU that you know you're going to need. All right. And so how do we know we're going to need something? How do we know we should save it even closer to the CPU? Well, we're trying to take advantage of something called locality. A lot of programs, pretty much every program under the sun, accesses memory in a very similar way, in a couple different similar ways, all right? And we call that way locality. There's a couple common kinds of locality that caches optimize for, that make programs faster, all right? So the first kind of locality that you commonly see in pretty much every program under the sun is called temporal locality. It's when you have a program and it accesses the same variable over and over again. It's a very common thing to do, right? To keep talking about the same variable, going back to it. So, like, you can imagine that every single program in the world has a for loop, right? Int I equals 0, I is less than whatever, I plus plus. So this kind of thing, like there's a million of these in every single program that's ever written ever. And so let's try and optimize it, like, because you know you're going to come back to this variable I. You're going to read it, write to it. I is 0, now it's 1, now it's 2. You keep coming back. That's called temporal locality. Programs are pretty much always going to do this. They're always going to access the same variable. So let's keep it a little closer to the CPU, even if it's not able to be saved in a register. Let's keep it a little bit closer. Let's take advantage of temporal locality. And then let's also take advantage of something called spatial locality. And this is when you have a program and it's not coming back to the same variable, the same place in memory per se, but it's coming close. It's accessing something very close to that thing you just accessed. And that's a very common thing to do. For example, in this loop that we know we have a million of in all of our programs, how about we read from the indices of an array, going bigger and bigger. So you see how we're never coming back to r of 0, but we're eventually going to read something very close, right? In the next round of the loop, we just read r of 0. We're going to read r of 1 next. And we're going to keep on going in this way. So wouldn't it be nice if you ever access r of 0? Like, maybe save, like get ready and like get in a special place called the cache. Let's save r of 1, r of 2, because we know we're going to need it later. We know we might need it. And so let's get it a little bit closer to the CPU if we can't put it in a register. All right. So how do we optimize this? So here's some takeaways. Right. We can make our programs faster if we store commonly accessed memory closer to the CPU. If we store I in a register, we are set, right? But maybe we don't have enough registers for that. Let's at least get it out of memory. Let's get it closer than memory, closer to a register, right? Closer to the CPU. So that's takeaway 1. That will take advantage of temporal locality. Key takeaway 2, we can also get a speed up by not just loading r of 0 into a register or saving it closer in this place called the cache. We can gain a speed up by loading a chunk of memory closer to the CPU and instead of just 1 byte. Instead of just this int 4-byte thing, let's load a chunk of memory closer to the CPU because we know we're going to come to these guys later. That's pretty nice, isn't it? So yeah, caches, for example, load that chunk. Caches are a place in memory in between the CPU and the RAM that is a little bit faster to access than main memory, and it remembers these things. It takes advantage of these kinds of locality. All right. So here's what happens. We're storing I in the cache. We're going to store a chunk of memory in the cache so that it's ready and it's closer when we need it. Okay. That still probably sounds a little bit vague. I promise that I'll show you a program that takes advantage of the cache soon. Probably not today though. So here's the hierarchy of memory. Finally, I can get to the slide that has the picture of what we need to talk about. So here's the setup. All right, we have at the tippy top the fastest thing we could ever access. It takes 1 clock cycle because it's on the CPU. We have 32-ish registers. All right, that's all we get. If you need more things saved away, you can't use any more registers. But they are the fastest thing to access, and it costs like $20 to make a register, for example. It's expensive, right? It's expensive, but it's very fast, all right? And then caches, they are on the CPU. They're just farther away from the processor, the processing part itself. But they take a little bit longer to access something that's stored in the cache, right? So it's better than main memory, but it's not quite as good as a register. So you can store on the order of a few kilobytes of things in a cache, and that's located on the CPU still, but it's a little bit farther away from where the action's taken place, so it takes about 10 clock cycles to get something out of the cache. So it's still better than anybody down here, all right? So it's very expensive to build a cache as well, though. So you got the order of kilobytes in your cache, like a 32 kilobyte L1 cache. Maybe you've heard of that before. And then, all right, if something isn't there, you got to go looking in the main memory, right? You definitely know it's there if your program's running. It's in the main memory for sure, but we like to copy it onto the cache when we can. And you have the order of gigabytes, right, in your main memory. And it's still farther away. This is definitely not on the CPU anymore. It's still part of your primary storage, your main memory, but it takes about 100 cycles just sitting, twiddling your fingers, trying to wait for something to happen. So it takes a while to get something out of main memory. It would be nice if it was somewhere closer, and so that's why the caches exist. All right, and then everybody else down here, an SSD, for example, is a flash kind of storage. You can store on the order of terabytes. That's what people commonly have these days. And it's secondary storage. It's much farther away from the CPU. It's much slower to access. It takes about 1 million clock cycles to get some information out of your disk, even if it's an SSD. If it's a spinning hard drive, multiply that by 10. It takes even longer. It's disgustingly long. All right. So that's why we have this hierarchy. Get things closer to the CPU when we can. Save things for later, even in this place called the cache, right? because then we don't have to talk to main memory, then we don't have to talk to the disk as often. And then way on the bottom, of course, is stuff even farther away than a spinning hard disk, like on the internet, for example. Like you're talking to some other computer which has to load stuff out of their own hard drive and then send it through the pipes of the internet, which has some latency. Oh man, that takes forever. So when we can, we move stuff to primary storage for sure whenever we run a program. And then when we try and access memory, we want to keep it closer than even main memory. We put it into the cache. We put it into this thing called the cache. There are different kinds of caches. We put it in one of them at least, and that keeps it as close as possible to the CPU before we have room to place it in a register. Okay, so that's kind of the story. That's what memory is all about. Where we have a bunch of different levels that have different access speeds and costs, and it helps us get the best bang for our buck. Okay, so definitely read the chapter as well. This is like the zoomed out version of everything, but hopefully that makes a little bit of sense. Do come to office hours. Do yell at me if it's not clear enough. But yeah, let's keep on trucking, because at the tippy top, right, we talked about everything up until registers. Registers are like the fastest kind of memory, if you think about it, right? It's closest to the CPU, it's ridiculously fast, and because of that, the way that you make a register is different than how you make a cache or a main memory. Like it's made out of different hardware, and it costs a whole lot more money, all right? So it's honestly great that we get 32 registers. Like some people, like back in the day, even a decade ago, we were all in like 32-bit x86 land. It is like back then you only had like 6 registers to work with. Everything had to be like you had to wait for memory. You had to use more memory because of that. Things had to be saved in RAM and hopefully the cache. But oh man, those were the days, right? So consider yourself lucky. You can, for the most part, when you're writing assembly in this class, you can get away with just like putting everything you need in a register. It's probably as fast as it could be. Okay? But yeah, the second you need to store more than 32 things, you have to use your memory. And then the caches are getting loaded and stored for you. So the cache is an automatic thing. It's a place that's like getting automatically loaded into. So like the second you talk about a variable, it's placing it in the cache. The second you load an index from an array, it's loading a whole chunk of that array into the cache. All right? So yeah, keep reading about that, but that's kind of the story. All right? If we go back to this picture, you see this bus has a bunch of different things, and I mainly talked about like the CPU's doing the orchestration. Like it's all right, I am going to send, hey, read to the memory unit, read this address, and then it's sending stuff back along the data bus. It's usually the CPU that's in charge, but it doesn't have to be, all right? Because we just learned that it's really, really slow to ever talk to memory, so we kind of want to minimize that if we can, all right? In the past, the CPU really was the orchestrator. It was the only person that could talk to memory. The CPU had to like say, all right, I want this, and you give it to me. All right. Back in the day, that was true. It's no longer true. All right. And that CPU, when it was doing that, it had to wait, right? Because it needed this memory before it could do anything else. It needed that thing at that address, and it just sat there. Nowadays, we can be a bit more smart about it. There's something called DMA, or direct memory access. It's a way for devices to talk to memory by themselves. So it's a way for this kind of thing to happen. An output unit. Like say you double click a program, the CPU can set off the process of reading from the hard drive into memory that program, but this kind of thing can happen along the data bus. All right, they can talk to each other. Devices can talk to memory on their own and send data, which is really cool, and that saves the CPU time, right? It can be doing other things while that stuff is getting loaded into the main memory. Isn't that really cool? And so that's great for devices that are always spitting out information, like probably your hard disk, definitely your Ethernet cable, for example, your internet, your Ethernet card, all that stuff. It's very nice that it can just go straight to memory when it needs to and not have to get the CPU involved. The CPU can do math on other things while it's waiting. Okay, so this is not really something we're going to control in a CSCI 45 class, but it's something that exists, and it's good to know about. All right, so that's DMA. Let's talk about just instruction set architectures in general, because why not? We'll learn about the von Neumann architecture. you have a bunch of different kinds of instruction set architectures, right? You've got Intel x86, you've got ARM, and you can have different adjectives that describe those architectures. ARM is a RISC architecture. Intel x86 is a CISC instruction set architecture. But like in general, like what is an ISA? What does that even mean? All right, so an ISA in general, an instruction set architecture, it's kind of like the language that the CPU speaks. All right, it's the encoding of the instructions. It's the ones and zeros that particular architecture is agreed on. Like, if you give me a 32-bit instruction that starts with 1011, I know that that's an add instruction in 64-bit ARM land. Like, that's what everybody's agreed on. That's what it means to be an ISA. That's all it is. It's the language that the CPU speaks. Because like on Intel, you send the same 32 bits to an Intel processor. It's like, I have no clue what you're talking about because 1011 doesn't mean anything to me. It's speaking a different language. All right. So it's essentially the language. It's the encoding. It's the bitwise encoding of what each instruction is. And like in Intel, like you can have a single byte that is an instruction. And ARM has no clue what that means, of course, because those don't even exist in ARM processors. So that's kind of what that means. And also, in ISA, just at a high level, it defines a bunch of things. It defines the kinds of data types that you can talk about. Like, all right, this instruction set architecture knows how to talk to and mess with 32-bit ints, but not 64-bit ints. Tough luck. Stuff like that. It tells you which registers must exist. Like every single ARM, 64-bit ARM architecture must have the registers X0 through X31. Those must exist, all right, in some way. Really X30, right? And yeah, it tells you the things that must exist, the way that you get to talk to main memory. We'll get into that. All right, you have your load instructions. All right. That's what it means to be an ISA. It tells you all the things that you could do. These are your instructions, and this is what happens when you run each instruction. Okay, so let's look at the 32-bit encoding of some of the instructions we know. There's a program called objdump, which takes a compiled program and it can dump it back into assembly. It can take and it can show us the bytes that correspond to each individual assembly instruction. So we have every instruction takes up 32 bits. For us, 32 bits per instruction for us. All right, so we're going to do objdump-d on a program. Which one should we do it on? Let's do it on one from last time for sure. Let's do it on just like our Hello World program. I think that would be a good one. Yeah, so let's copy that into today. So let's copy lecture 2's, I think it was hello, just hello. No, it's hello world.s, and I did something weird with the exit, right? No, sorry, copy it here, and then let's look at it. And I did this whole branch to the exit thing. Let's just put the exit back in the same file. So let's copy in lecture 2's exit. I'm going to just call it exit.s, yeah. So this bad boy needs to go here. Just put it in the same file rather than branching. So here is our hello world program. So here I have saved it. Let's I don't know if I need to use -g because we're just going to dump it anyway, but I'll do it for fun. Let's do -g just in case you ever want to load this into GDB. But we're going to do objdump instead. So I'll do as-g hello world.s -o hello world.o, and we have ld. You can also do -g on that. Hello world.o. Just call it hello world. And so there's my final executable program that just prints hello world to the screen. But we can objdump that, and that will spit out the binary encoding of each of these instructions. You can get it out of the actual assembly. Get it out of the machine code, because you know, right, when you look at hello world, the executable file in an editor, it's garbage because it's ones and zeros. But objdump can like decompile and understand what's going on there. All right, so objdump -d for dump and for decompile. Get it back into assembly for us, please. Take the bytes and tell me what's there. Hello world, and then it spits it out to the screen, but let's save it into a file. I'll call it hello world disassembly. That's the technical term. When you have an object file, you have something that is executable, you can disassemble it to get it back to assembly. Because all it is it's the ones and zeros that encode the assembly. So here it is. Here's my program disassembled. And it looks a little bit different, but this is what was stored in the binary itself. And here's what's going on. So all of these instructions make up our program. And you see how it converted it to hex because it didn't know. Like here's our 64. That's our syscall number for write. Yeah. And so this move instruction, for example, this is its binary encoding. This is the hexadecimal 32 bits of it, right? Here's the first byte of the instruction, D2 800808. You see that? So that's it. That's our move instruction. And then here's another move instruction. Let's move into a W register this time. And yeah, that's what's going on there. Interesting, interesting. Here's another move on an X register. You see that they both start with D28, even D280, I guess. That's pretty cool to think about. Move into a W register. These guys, they start with 528, it seems, 5280. And yeah, that's the encoding. These are the bytes that actually encode, and that's what the CPU sees, and it executes. It's like, all right, I understand that this is SBC 0 because these bits correspond to that. That's what the ISA has agreed upon. Isn't that cool? So that's that in a nutshell. I think that's fun to think about. And with that, let me teach you how to access memory in assembly. Let's do it, all right? Let's access memory in assembly. I know we did it a little bit already. We've used the data section really quickly, but let's go in more detail, all right? We know our loads and stores, but let's go a little bit in more detail. And to get started, let's just remember what memory is, right? It's just that big table. And it's taken 64-bit addresses, right? 64-bit numbers to byte values, and every byte is just 8 bits, all right? So your big long table looks like this. It's taken addresses, 64-bit numbers, to byte values, byte vals. And so here's your giant table. It looks like this, and it goes on forever. And yeah, the first address is 0 where you could store stuff, and it goes all the way to what you need, right? So if you want to load something, you have to know its address. If you want to load a multi-byte thing, like what if you want to load an int, which is 32 bits long? If you want to load multi-byte data from memory, yeah, you need to know where it starts, because it takes up contiguous addresses after its starting address, all right? So let's see. Dun, dun, dun. And I should put a /8 here, all right? Because it depends. So let's say we say load into a W register from, I don't know, an address stored in X1, for example. Let's say that X1 holds the address, it's address 42, and we want to read into a W register because we think that there's an integer there. So read 32 bits, read into a 32-bit register, but it's always a 64-bit address, all right? So this will read 4 bytes. Reads 4 bytes. If you read into an X register instead, it will read 8 bytes because that's how much room there is in that register, right? So the CPU knows, if you have a load instruction, it knows like I'm going to take either 4 bytes or 8 bytes depending on if you put a W register here or an X register here. And so, all right, if that's what X1 was holding, it held that address, well, it knows to go and look at address 42, 43, 44, and 45. There must be an int there somehow, and who knows what it holds. Maybe it also holds the number 42, something like that, right? Or maybe it holds the number 55 or something. And then you can also, in addition, there is a way, and I'll show you how soon, but if we're reading from address 42, we're going there and we're looking at all of those addresses, 42, 43, 44, and 45, if we want to read 4 bytes, reading into a W register. If you want to read just a single byte, like you want to go to address 46, like you can put a single byte there, 47, 48, 49. You can put single bytes there. Da-da-da. But I haven't shown you how. Right? There's no, because all I've shown you how at a minimum is you can do a store from a W register into memory, and that would put 4 bytes at once, and that's too many. How do you store a single byte and load a single byte? Like get this, just the 2, the 8 bits that correspond to the number 2. How do you do that? There is an instruction for that, and I will show you in 2 slides. All right. I want to just talk about load and store for a second, because there are some cool ways to load and store that I haven't shown you yet. So, okay, first of all, there's two kinds of loading and storing. There's loading and storing from a W register, and then there's loading and storing loading and storing into a W register and from a W register, and then there's loading and storing from or into an X register. And so if it's W, you're loading 32 bits, or if this were a store, it would be storing 32 bits, because that's how wide a W register is. If it was an X register, you're talking about 64 bits. So just remember that. The rest of these I'll just be talking about X's, but you can imagine that this first thing could have been a W register. All right. So the way that you know how to load and store looks like this. This is what I've shown you so far. Right? You have an address stored in this this operand register, X whatever, X2, whatever you want to call it. You put the brackets around, that's dereferencing it and storing whatever it finds there, the 64 bits that it finds there, into this destination X register. So it's essentially this encode. These numbers could be real numbers. It could be like X0, this could be X1. So there's an address in X1, dereference it, take 64 bits, shove it into X0. That's kind of what that means. But this is the syntax you'll see in the documentation. So that's why we're doing it this way. All right. So that's what that is doing. Let's see. You could get a bit fancier though. There's more than just this. If you're reading from an array, you don't have to add. You don't have to add to your address. You could do an offset. You could have an immediate offset when you're loading in your load instructions, and that's what this is. All right. So instead of just go to this X register and dereference the address, you could offset that address that you see in that register and then dereference. Isn't that cool? So a good example of that would be all right, let's load into, I don't know, W1 from X3 offset by 4 bytes, something like that. That's something that you could do. So it starts at the address in X3. Let's have some actual numbers here. Let's say that X3 holds address 42, and then we're eventually going to put something in W1. Who knows what's there right now, though. So here's what's going on in memory when you say that particular instruction. So here is address 42, 43, 44, 45, 46, 47, 48, 49, ... And let's say, starting at address 46, there's an int, right? Because that's essentially what we're reading right now. X3 is address 42, but we're offsetting that by 4 bytes. And so please go to address instead, address 46. Yeah, this is talking about address 46. And we want to read, so we're starting here, but we're offsetting by 4. So that takes us to address 46. Excuse me. And then we'd like to read into a W register, whatever thing we find there. And so we're taking 4 bytes, right? Because W registers are 4 bytes long. So we're going to take up the next 4 addresses, starting at address 46. 46, 7, 8, and 9. Go find your value. Maybe it holds 123 there in those 4 bytes. And shove it into W1. That's what that works like. And so if this were an array, you can just be all right, do this load. That's index 1 of the array. And if you had this in 8, right, that would be the next int. And so you could do it like that. It's a bit faster. So that's an immediate offset, load and store. So I'm just putting load here, but you could also have this be a store, and it would work exactly the same. Instead, you're storing into this offsetted address. Okay, so that's what's going on there. You can only have so many things in an immediate. You can only go up to 255 or something. If you needed a larger offset, you could store that offset in another register, and you could do it like this. So this is load into this destination register. Here's your starting address. Offset it by whatever number is here. It could even be a negative number, and then dereference that. So it's compute this address with xn plus xm, dereference that, and store it into the destination register. That's pretty nice to have that option. I think we'll use that eventually in this class in an example. And then you have an even fancier one that you'll use this so much when I show you how to do loops, because it does an offsetting for you and it saves it. Otherwise you'd be using multiple instructions to do the same thing. So this is really cool. I don't think I'll ever do it for you in the class, but it's something you could do in a lab to save yourself some time. What this does, this is the equivalent of 2 instructions, a load instruction and an add instruction. So this is really cool. All right, so this is load into the destination register, do this offsetting, xn plus 4, dereference, put it there, and this exclamation point at the end means also take whatever this address was and add 4 to it, so that the next time I come, I'll offset that by 4. Isn't that cool? So that's the idea. All right, it's making sure it's both loading and then like offsetting. It's kind of like go to R of I and then I++, essentially. That's what that would be translated into, essentially. So that's really cool. You don't have to use it if you don't want to, but it's very fancy, and it saves you 1 instruction, essentially. That's how would you do this otherwise? You'd have to do a load without the exclamation point and then do an add, right? Add into xn, 4. So it's saving you a clock cycle. Program's twice as fast if you're just running that thing. All right, so that's that. And then here's how you store individual bytes. So how do I go to address 46 and actually store it? Just 1 byte, please. There's an instruction for that. It's load byte and store byte. LDRB, STRB. Okay. These, because your registers, you only have, your options are X registers and W registers if you want to work with data inside of your CPU. We're going to work with W registers. These instructions only work with W registers, and they only ever look at the rightmost byte of those 32 bits anyway, the rightmost 8 bits. So, okay. An example will go a long way here. So let's use load and store byte in an example to convert the word CSCI. I'll have lowercase CSCI. I'll put that in my data section. I'll make a string that says lowercase CSCI, and we'll convert it to all caps CSCI, loading a byte at a time and doing some math. All right. So let's get that set up, and then I'll show you what I mean. So I'll make a program called all caps. Let me oh shoot. Let's do hello world. Let's start with that, and I'll steal it, and I'll turn it into another program called allcaps.s. All right, so let's put a string in the data section instead of hello. Let's have it be CSCI. So CSCI, I'll make it at the label called CSCI, and then I'll keep the new line. Why not? But I want to change the first 4 bytes of CSCI. All right, each byte at a time, convert the lowercase c to capital C, lowercase s to capital S, and so on. All right, so what are we going to do? I'll eventually print it back out, so I'll keep the stuff down there for now. We'll change it up a little bit later, but here's what we want to do. Let's capitalize the CSCI string in the data section. All right, so what do we need to do? We need to get into a register each of those bytes. So let's say in X0, we're going to have that store each individual byte address, because every address still needs to be an X register. This is a 64-bit machine after all. So here's the CSCI string essentially in memory. It's lowercase c, lowercase s, lowercase c, lowercase I, and more. But that's all we really care about. And let's pretend like this starting address was address 100, this is address 101, 102, 103. So our job, if we want to capitalize it, is to like stick address 100 in a register, because now it's pointing there, go load that byte into another register, capitalize it, and load the capitalized version back. So like take this, make it capital C. That's kind of the idea, all right? That's the idea. So that's what's going on there, and we'll have to like put it somewhere else, like put it in W1, because we have to use W registers for our load bytes and store bytes. Like here's my lowercase c, make it capital C, and then shove that back at that address, and then move on. Now go to address 101, and do the same with the S. So that's kind of the process, right? So how do you capitalize? First of all, how do you even capitalize one of these letters? We can do ASCII math, because lowercase c, lowercase c is the number 99 in decimal. That's ASCII encoding in a byte. Lowercase c is 99, capital C is 67. And then S, let's do S. There's a pattern here. Lowercase s is ASCII code 115, so it's the 1 byte encoding the number 115. We see the number 115, we know it's lowercase s. We want to make it capital S. To make it capital S, you got to make it 83 instead. There is a pattern there because these letters go in order. They go in order for the capitals as well as the lowercase. It just so happens that the difference between the lowercase letters and the capital letters is 32. So if you have a lowercase letter, like this is the number 99, we want to make it 67. You just got to subtract 32 from every character, because every character is secretly a number. Subtract 32 to capitalize. Isn't that cool? So yeah, what we want to do, get each character into a register, subtract 32 from it, I guess, and then store that back where we found it. Now it's capitalized in memory. All right, so that's the goal. Well, let's make that happen. So what we want to do is load we need to get the starting address of the CSCI string. Load the address of the CSCI string into x0, I think is what we decided on. And so that's going to be this load instruction. Load x0, and it's equals CSCI. That's like your ampersand in assembly land. So now the address of the CSCI string is loaded into x0, and remember that the address of the CSCI string is the address of its first character. It's the starting address. All right, so we got that going on. And now in x0, that's like address 100, we have that address. Well, let's load from that address and get whatever character was there into W1. All right, so let's capitalize the first character. And so let's get it. Load a byte into W1 from whatever x0 is looking at. So x0 holds an address. Go there, read a single byte into the lower byte of W1. It's not using all of it. So that's what's going on there. And now it works. Now W1 is going to hold that character. Remember that x0 holds the address of the C character. So we just read the C character essentially into W1. All right. So W1 is, remember that W1 is part of x1. Let's not forget that. So just for fun, just for review, W1 is the rightmost 32 bits of x1. But the load byte needed that W. Load byte can only handle W registers for some weird reason. And then, all right, we've got the character in W1. Let's subtract 32 from it using the sub instruction, the sub assembly instruction. Sub from W1 the number 32. That'll capitalize it. Subtract. Now it's capital C. 32 from W1 to capitalize. And then now we've got capital C stored in W1. We want to shove that capital C back where we found the lowercase c, back in the actual string memory. So that's where x0 is pointing to. All right. So now it's going to be a store byte. Store a byte from W1 into wherever x0 is pointing to, and that's updating that C character. So that we went into memory down here, changed this lowercase c to a capital C. That's pretty sweet. So store the capitalized character into the same address I just read from. And so that's the process for the C. And sadly, I haven't shown you how to loop yet in assembly, so we have to copy and paste this 4 times. All right? Though we need to advance our pointer, because x0 right now is holding address 100, for example. The next character is at address 101. It's the next byte over, so the next address over. So let's add 1 to x0. Go to the next character by adding 1 to x0. So add into x0 the number 1, because the next character is 1 byte away. Is at the next byte in memory. So yeah, if you forgot pointers, this is going to force you to remember doing this kind of low-level stuff. All right, that's what assembly is all about. So now we're ready to capitalize the next character. Whee! So let's take this, I'll get rid of that, It's not the first character anymore. So let's call it next char. And this is the address of, like, let's just say it's the address of the next character. It's really the S, this one. But I just want to copy this a couple times. So there's that. That's kind of capitalize the S to a capital S. And then we want to get ready for the next C. So we did the C, the S, get the address of the next C now. We just did these guys, that guy. Then we want to go to address 102, so we'll advance the pointer again. Capitalize what we see there. Advance the pointer again. So that now we're ready to do the same stuff. When we do the same stuff, we're capitalizing the I, right? Capitalize the next character. Now finally, this is the last character. It's been capitalized. That's capitalizing the I, right? We keep advancing x0. I could have done the cool thing, like the number sign 1. That could have worked. But this way's easier to understand when you're first learning. And so now, sitting in memory, we have capital CSCI. Let's take advantage of that. Let's look at the fruits of our labor. So let's print our CSCI string. Whatever's there. Hopefully it's been changed. Let's print out our CSCI string to the standard output. So we've got the write syscall set up pretty much, but we want to print to standard out the CSCI string. And there's only 5 characters if you include the new line. So not 14. 5 bytes that you want to read from there, and go to file number 1, please, and then exit the program. So that, my friends, should do it. So let's assemble it. All caps.s -o all caps.o, and let's link it all caps.o into a final executable just called all caps. Boop. And if we run it, it should capitalize the stuff in memory, and then go to that same memory address, see what's there now. Oh man, it's capital CSCI and a new line. Sweet. So that is the cool example of the day, and I think that's where I want to leave you. So please take the rest of the time that you would normally be watching a lecture to work on the lab and all the reading that you have out right now, and I'll see you in the next one.